Okay, welcome to the afternoon session. So we have two talks in afternoon session, and the first talk will be Ryohei Kobayashi from University of Tokyo, and he'll talk about automorphism in the gauge theory and Clifford-hierarchy stabilizer code.
Okay, thank you for introduction, and thanks so much for invitation. It's my first time to be in Korea, and it's very good to go back to Asia from US. So first of all, I'll be talking about some automorphism in some gauge theory of the finite group and its relation to the logical operators in the Clifford stabilizer code and its generalizations. So my talk is based on the my pair of talks, mostly based on these papers that is done with Paul Shen and Guan Yu, one of the collaborators here. And both of them are about the Clifford stabilizer course, but I also mentioned some more previous work of mine that considers logical operators of the Pauli stabilizer course. Okay. So since Guan Yu already talked about the LDPC part of the story, so I'll be mostly focusing on some topological code. Maybe some of you might feel bored, but sorry about it. But okay, I'll still say something non-trivial we can say about the logical operators of the topological course. All right. So it is by now become very familiar that the logical operators of the quantum error correlating course corresponds to the global symmetry of the underlying theory of the quantum many-body systems. So like for instance, if you take a surface code or a toric code, like all of them are just like a quantum many-body systems, and we are using the ground sets of such many-body systems, and its symmetry, its emergent symmetry is like it doesn't change, it leaves the ground state Hilbert space invariant, and therefore it becomes logical operators, right? So I found this slogan of identifying the logical operators to the symmetry of the theory to be very, very useful, and it can be used to find many new logical operations of the quantum error correlating course. So let me just start with a very fundamental example of the Z-toric code that everyone knows. And so in the Z-toric code, I think the very familiar logical operator is just like a Pauli Z operator or Pauli X operator. It just corresponds to the string of the anyons, right? Like a Pauli Z operator corresponds to the string of Z, and the Pauli X corresponds to the string of X. But it's not the end of the story. There are many of the nearly transversal or constant depth unitary operator that generates the logicals of the toric code. For instance, one funny example is like a Z toric code has an ordinary global symmetry which exchanges the E and M. So this is some automorphism of anyons, right? And so this is sometimes called the electromagnetic duality because it exchanges the electric and magnetic thing. And so there are many ways to implement such electromagnetic duality in the Z-toric code. One way to do this is, most easiest way to do this is just a translation associated with a transversal Hadamard, so that it exchanges the bracket and star operators. But actually there are many ways to implement. And the one way to do this is exists a constant depth circuit which actually generates electromagnetic duality. Let me just show you for fun. Here's a circuit, explicit circuit which generates E and M duality. It's actually a depth 3 circuit. So is this some pointer? Maybe we can use it. There's some a depth 3 circuit, like a product of the 3 unitary circuits. And by the iterative action of the unitary operators, it induces it induces some internal exchange of the X and Z stabilizers instead of the translations. So this is a kind of some sort of the internal induces some sort of the internal action within the X stabilizer and the Z stabilizer within this rectangle, and it actually generates a EM exchange. So there are many these kinds of some internal symmetry operator or some logical operators of the Z-toric code, and it's fun to explore these logical operators in the generic setup. By the way, feel free to ask many questions because I'm afraid that my talk is a bit short. So Okay, so we are of course interested in the logical operators which like preserves like a fault tolerance, right? So like we are mostly interested in the transversal gate or like it's a slight variation of that. So like in my talk, I'll be mostly focusing on the constant circuit. So it's as good as a transversal gates, right? Like because it doesn't really propagate errors. So like we are interested in such a like some symmetry of the quantum codes generated by the constant circuit. And so Ziwen's talk was mentioning, like there's some trade-off between the non-Cliffordness of the like logical action generated by the constant circuit and some dimensionality of the quantum error correcting codes. So it is known as a Bravik-Koenig bound. It was mentioned in the Ziwen's talk actually. So let me briefly recall what a Bravik-Koenig bound was about. So like in order to introduce the Bravik-Koenig bound, we need to introduce Clifford hierarchy, right? Clifford hierarchy is just a hierarchical structure of the unitary operators. So like a first level of Pauli, second level is Clifford, and then like we can inductively define the some set of the unitary operators. And the like n importantly n equal or larger than 3 are non-Clifford operators. Okay, and it can be defined inductively. For instance, like a third level, it contains like a CCZ or CSOT, and they become non-Clifford operators. And then the Bravik-Koenig bound basically says that if you have some local topological Pauli stabilizer code, we need at least an n-dimensional operator to realize the nth level of the hierarchy by the if we want to generate some logical operator by a constant circuit. So that's a dimensionality bound on the how non-Clifford it can be. Okay. Okay, so this is a Bravik-Koenig bound, and so let me just show you like what kind of logical operators we can get with the Pauli topological stabilizer code. So like due to the Bravik-Koenig bound, like if you want to like realize like a native nearly transversal logical operators by the constant circuit, we need at least 3 dimensions to realize it. So like there are like a bunch of the examples. Like maybe this one is more familiar because it's associated with the color code. So like take 3 copies of the Z2 toric code in 3 dimensions. In that case, there are like a bunch of logical operators which is aligned with the Bravik-Koenig bound. Like for instance, a 1-dimensional, just a string operator which corresponds to Z. And there are 2-dimensional operators which corresponds to Pauli X and control Z. And then like there's a control Z operator which corresponds to the cup product generates the third level of the non-Cliffordness. Okay. And then like a slightly more exotic example I like is some single layer of the Z2 toric code. We don't need to take copies of the Z2 toric code. So let's just consider a single layer of the Z2 toric code. But the caveat is like a particle is not fermionic instead of bosonic. So like finally, so if you change the statistics of the particles from the bosonic to fermionic, like it turns out that there are much more like a richer class of the symmetries we can talk about. And so let me just show you here. So like the first and second level is roughly the same. So like first level is just like a string of the anyons. It's just a Pauli Z. And the second level is basically like a Pauli X or CZ. But the third level, we can generate the non-Clifford operators with just a single layer of the Z2 toric code. It corresponds to the control Z or control SOT, depending on what cross manifold you are talking about. So like here I'm talking about like some like variants of the Z2 toric code, which can be defined on a generic 3-dimensional manifold, and depending on topology of the like underlying 3-dimensional manifold, like it can generate many different kinds of the non-Clifford operators. So so basically, like in such a Pauli stabilizer course, maybe Guanyu was mentioning a little bit in his talk, but like these non-Clifford logical operators basically corresponds to some so-called SPD defect. Like I would say it's a gauged SPD operators, which is already mentioned in the Guanyu's talk. So like at the level of just a topological course, like such a non-Clifford operators defined out of the cut product has a very, very deep relationship to the like a symmetry protected topological phase. So let me explain a little bit. So gauged SPT operator means following construction. So like we start with some some paramagnet with a G symmetry. Like let's say the Z2 times Z2 symmetry. Like we just have some paramagnet whose whose stabilizer is just a power X, just like a bunch of power X. And then let's say we put some symmetry protected topological phase, like a cluster state protected by a Z2 times Z2 symmetry. And then with this decoration of the symmetry protected topological phase, we can gauge the Z2 times Z2 symmetry. And after gauging the Z2 times Z2 symmetry, we end up with a Z2 times Z2 gauge theory, which is basically two copies of the Z2 toric code. But here, initial decoration of the symmetry protected topological phase ends up with some defects of the Z2 times Z2 toric code. And this is some symmetry defects of your theory. So if you basically pump these symmetry defects, you get some action of the symmetry operators. So there is a correspondence between this 1 plus 1D SPT phase and some two-dimensional symmetry operator. So that's how we can go between the SPT and the logical operator. Okay. So speaking of this three-dimensional fermionic toric code, it can be regarded as starting with some fermionic phase with a fermion parity symmetry, and then gauge the fermion parity. Then you end up with some Z2 gauge theory of the fermion parity symmetry. So here, a corresponding logical operator is some fermionic topological phase. So here, in one dimension, so there's some fermionic topological phase, which is a Majorana chain. And correspondingly, there's some two-dimensional logical operator, which generates a control Z or S, depending on the shape of the manifold. And then in three dimensions, there's some fermionic topological phase, which is a P plus IP superconductor. And if you basically pump it through your system, you get some non-Clifford operator. It can be like a control Z or control S or T. Let me just show you the logical action of this pumping P plus IP superconductor in the a fermionic Z2 toric code. It becomes some combination of the control Z and control S and T. Okay, so its logical action really depends on the topology of the manifold. So the first part really looks like a usual cup product construction of the triple hyperproduct or something. So you have some level of the logical operators like a J and K and L. Its logical qubit is labeled by the first cohomology of the manifold, and then taking triple cup product corresponds to control Z. But here, this P plus P superconductor has some additional contributions like a control S and T. So here, a technical comment is that this contribution of the control S and T doesn't really require the triple intersection of the cycles. So it's slightly more general than the a usual control Z gate people talk about. So I hope that this kind of construction logicals can also give rise to some interesting gates in the quantum DPC. But so this is what we can do in the fermionic toric code. It's slightly different from a usual bosonic toric code. It is just a comments about the power stabilizer code. Okay. So is there any questions so far? So then I will try to go to the non-Pauli stabilizer code. Okay, so in the rest of my talk, I will discuss how the non-Pauli codes can surpass the bounds of Bravik-Kenny type bounds with the help of the so-called automorphism symmetry. So the outline is that we first introduce some automorphism symmetry in the twisted gauge theory, and then several applications of that. It includes some non-abelian version of the cell-quality memory, which is mentioned in the Guanyu's talk, and also the some Clifford-hierarchy stabilizer code, which has transversal non-Clifford operators in the two dimensions. Okay. So all right. So we can go beyond the Pauli codes from now on. So the Pauli codes is, so as you know, this basically corresponds to the abelian anneon theory. And at the level of the gauge theory, for instance, the toric code surface code just corresponds to Z2 gauge theory. So these basically realize abelian things. But if you start to go beyond the Pauli course and talk about the non-abelian, so non-Pauli stabilizers, we can start to talk about like a non-abelian anion systems together with some like a non-abelian gauge theory, like a G gauge theory with a non-abelian gauge group, or some abelian gauge group, but abelian gauge theory, but with additional some twist, which after all corresponds to the non-abelian anion systems. Okay. So like for instance, the Clifford stabilizer code I will introduce corresponds to the Z2 cube gauge theory with a twist. And the Allison will talk about some quantum double model, which corresponds to the G gauge theory with non-abelian groups. And the for instance, I forgot to put the citation here, but for instance, Tyler and other people talk about group-based surface code, which is basically the surface code version of the quantum double model. And of course, Guan already talked about the non-abelian version of the quantum DBC, which is also some variant of the twisted case theory put on some funny manifold defined out of the quantum manifold mapping. Okay.
Can I clarify, are you saying Clifford stabilizer codes are all gauge theory codes? Or just like the way you construct them, they happen to come from gauge theory?
Clifford stabilizer code can be defined in a more generic way, but here I'll be just talking about the twisted case theory. Yeah, it can be just defined as some, like each of the stabilizer Cliffords and then like there's some non-trivial logical space. It's just similar to frustration-free Hamiltonian. Yeah, doesn't have to commit with each other. Like for instance, these XCZ guys doesn't commit with each other, and it's committed becomes some other stabilizers. So it's very different from a Pauli, where everything commit. Yeah. Is there other question? Okay. So right. So I want to talk about some logical operators of the such a non-Pauli logical operators. So let me try to say something about the symmetry of the gauge theory, where the G can be non-abelian. So in general, just the physics context, if you have a G gauge theory in the space-time, in the D plus one dimensional space-time, there always some global symmetry, which is labeled by this one. So it's an ordinary symmetry, just a zero form symmetry. I'm not talking about a generalized symmetry. So the system always contains some gauge theory always contains this theory, this symmetry. So one of them is just one I talked about earlier. It's called the gauged SPT symmetry. It just corresponds to pumping the GSPT, like the construction I have already given. This group cohomology basically classify the bosonic SPT phases. So it's just labeled by SPT classification. And then there's some additional symmetry I want to talk about. It's called just automorphism symmetry. It's just associated with the automorphism of the gauge group. So for instance, if you have a U1 gauge theory, there's a charge conjugation. And so this kind of the charge conjugation which reflects the U1, right? And such a automorphism corresponds to your symmetry of the gauge theory. And usually, if you just take copies of the toric course, there's automorphism symmetry which just swaps a copy. It's kind of boring because it just generates a swap. But if you talk about some non-abelian code with a twist, this automorphism symmetry starts to become interesting. Okay, so in the context of the just the Pauli stabilizer code, people always talk about the gauge SPT operators because this automorphism is boring. Everything discussed in literature and the Pauli stabilizer code is just like a SPT. For instance, the Bainey's paper, or there are many works which uses a cup product to generates a CCZ gate, but all of them basically corresponds to the SPT. But we can say do something interesting using the automorphism if you go to the non-Pauli course. Okay. It's an emergent symmetry in general. Yeah. So for instance, the gauge SPT defect is typically emergent symmetry. It corresponds to CZ. So it's just permutes stabilizers from the E to E times M or something like that. Yeah, M to M times E or something like that. So it's typically emergent symmetry. Okay. All right. So Okay, so let me try to say something about the application of the automorphism symmetry. Before doing that, so we want to talk about some generality of some gauge theory. Like in the gauge theory, we can always talk about a twist, like which basically corresponds to topological action, like Chern-Simons. If you have so in my talk, I'm interested in the finite gauge theory, which corresponds to the stabilizer code of the QID systems. And then we can add some twist, which is labeled by this group cohomology. And for instance, it's a old work of some generalized and quantum double model to the twisted setup, which is called the twisted quantum doubles. In this case, like a lattice model can be labeled by a pair of the objects, which is one of them is just a gauge group G. And the other thing is this omega, which describe this twist. For instance, other example is Clifford stabilizer code I'm going to introduce, which is basically just a Z2 cube case theory with some non-trivial cocycle. And this non-trivial cocycle enables a non-abelian topological order in these systems. Okay, so if you have such a twist, the automorphism symmetry starts to act non-trivially on the theory. So the twist is very crucial for enabling the non-Clifford action out of the automorphism symmetry. So let me try to explain why. So let's say we have some gauge group G with some topological action, which is omega. And then basically, I have said that a gauge group has a automorphism symmetry. So let's say we have some automorphism of the groups. Okay, so the boring example is just take two copies of a toric codes and swapping the copies generates some boring Clifford operators. Okay, but then suppose that so in order to qualify it as a symmetry, we need to preserve this automorphism has to preserve the labeling of your quantum error correcting code omega. This has to preserve the twist. Okay, so suppose that so we need to require that this automorphism induces some action of the group cohomology, but you need to require that the omega is preserved under the action of the automorphism. Okay, so it means that under the action of this law, this omega can be possibly transformed. But we need to require that this transformed thing has the same cohomology class as the initial group cohomology. So a shift is almost like a coboundary. Okay, so let's say this property is satisfied for the pair of the automorphism and omega, and then this law is your symmetry, the symmetry of your error correcting codes. And then if you have a non-trivial shift of omega by the action of the automorphism, the automorphism starts to act non-trivially on the logical space. So basically, the reason is that if you the automorphism symmetry has this kind of form. So it has a form of this V operator. This is just an operator which acts by some vanilla automorphism. It just acts on the group elements by the corresponding automorphism. It's basically just a transversal operator which acts on each qubit, and changes the group elements. But this is not enough to qualify as a symmetry because the omega is shifted by some boundary, right? And in order to compensate this kind of effect, we need to put some additional gauge SPT-like action, gauge SPT-like operator. So after adding this integral of alpha, it corresponds to some gauge SPT type cup. It can be typically expressed in terms of cup product. If you add this kind of operator, this automorphism becomes a symmetry. So the twist is very important to have make automorphism act by the non-Clifford action. So this integral of alpha enables a non-Clifford action and the interesting structure of the generalized symmetry of your gauge theory. Okay. So this operator generates some logical operation of your quantum double model or Clifford stabilizer codes. Okay. Okay, so let me just show you the example. So the example, one of the example is the non-abelian cell quality memory in 5 space dimensions. So this is what we have done with Portion and Guanyu. So as Guanyu briefly mentioned, it is also a twisted gauge theory in rather high space dimensions, five space dimensions. So this is the first example of the thermally stable non-abelian topological order. So the construction is as follows. So we have 5 space dimensions, and we have basically two-form gauge theory with this type 3 action. So twist is given by this guy.
That's a 40, you cannot have a thermally stable non-abelian.
I think so, yeah. Because the basically take is that we only can have a loop, and there's some argument saying that lowest dimensional stuff has to be abelian, like a loop has to be abelian always. So here a loop is indeed abelian, and the surface is some a two-dimensional object becomes a non-abelian fusion loop. So yeah, so like this. So this is a three-dimensional topological operator, and it fuses into some of the loops, something like that. Yeah. So this can be achieved. This cannot be achieved in the 4 dimensions. Okay. So so we have 5 dimensions, and this is actions. So it's very similar to the twisted some Clifford. So this can be realized by Clifford stabilizer model. Very similar to some non-abelian topological order in two dimensions, just a twisted gauge theory basically. But the interesting property is that because this is a two-form gauge theory, we don't have some line operator like a string operator that corresponds to the point like anyons. So the lowest dimensional object is some loop-like excitations. So the logical operator corresponds to this what I write as a W. It is just a product of the Z on the surfaces. So it's a two-dimensional logical operator, which corresponds to one-dimensional loop excitations in your topological order. And there's also some magnetic flux, like a Pauli X type object, which doesn't really correspond to the logical Pauli X operator. It's some non-invertible or non-abelian object, so which I write as M. This is a three-dimensional object. And the non-abelian fusion rule looks like if you fuse a pair of the M, it corresponds to some of the W's. This is a three-dimensional object, so dimensionality doesn't seem to match. But basically, the fusion rule is basically saying that if you fuse a pair of the three-dimensional things, it fuses into the sum of the two-dimensional things, which is inserted in the in an arbitrary way within the three-dimensional object. So this kind of a fusion rule is became kind of familiar in the context of a non-abelian, non-invertible symmetry in the field theory context. But we can achieve this kind of fusion rule in the stabilizer code as well. So since this is a twisted gauge theory, so this theory can be realized in the Clifford stabilizers. So this non-trivial twist requires us to introduce some Cliffordness of the stabilizers. Basically looks like X times CZ. This doesn't really have a particle, so basically the excitation is Boltzmann suppressed at the sufficiently low temperature, and it starts as it has a self-correcting quantum memory property. Okay. So this self-correcting memory also has interesting logical operators. So the logical operators comes from the automorphisms. So this twisted two-form gauge theory that corresponds to the self-correcting memory has a automorphism symmetry of the Z2 cube gauge theory. So basically, this automorphism just corresponds to like a swapping pair of the gauge fields. So we have 3 gauge fields, like a red and green and blue, similar to the color codes. And basically the automorphism is just swapping 2 qubits, that corresponds to red and green. And then this swapping red and green doesn't change the twist, homology class or twist, shift the twist by a coboundary. So this a swap of the 2 qubits actually corresponds to the symmetry of your quantum error correcting code. But because of this homology, because of this shift by coboundary, shift of the twist by co-boundary, actual logical operator of the Clifford stabilizer code becomes this guy. So now it looks like just a boring swap operator that exchanges some color of the qubits on the transversally. But additionally, we have some additional like a product of a control Z gate coming from this car product term. And this overall, it becomes a non-Clifford logical operator. And so if you put this cell quality memory on some 5-dimensional manifold, it indeed generates a non-Clifford control Z gate of the no-abelian cell quality memory. So okay, so this is a kind of interesting property because like a lowest dimensional like a cell quality code that achieves a transversal non-Clifford gate will be it has been known to be just a 6-dimensional color code, which corresponds to like a well, just a 2-phone gate series with a twist. But yeah, so we can achieve the 5 dimensions. We can achieve the non-Clifford gate in the 5 dimensions, and it indeed has like a good distance scaling compared with just like a cell quality color codes. So like for instance, since we have some 2-form gate theory in 5 dimensions, call distance scales like this while having a transversal non-Clifford gate. But like a cell quality color code, the usual 3-dimensional color code with a control Z gate scales distance scales like this. So like in terms of the distance scaling, it performs better, right? And so this is kind of the benefit of the thinking of the twist in the quantum error correcting codes and considering the automorphism. Like it helps us to surpass some bounds on the dimensionality of the where that we can achieve some transversal non-Clifford gate. And we will explain that this kind of properties some more general in the and also can be achieved in generic space dimensions. Okay, is there any questions so far? Okay, so let me try to explain the Clifford-hierarchy stabilizer code in generic dimensions. So what we can do is as follows. So like so at least we can find the following some Clifford hierarchy stabilizer code where each of the stabilizer is within the Clifford hierarchy. So we can find a family of such a Clifford hierarchy stabilizer code with the following properties. So so we can achieve the D+1 level Clifford hierarchy within D space dimensions. So this surface is a Brevikinic bound, right? And so we can do this kind of thing. We can achieve the we can basically surpass the Brevikinic bound by considering the non-Pauli stabilizer code. And this turns out to be very broad. Can be like a generalized to very broad result. Like yeah. So if you're interested, please see the Allison talk. So but I restrict myself to this family of the stabilizer codes. Okay, so as example, like a simplest example is of course the D equals to 2. So in D equals to 2, like there is a T gate within the third level of the Clifford hierarchy. Okay, so so in 2-dimensional space, we consider the Clifford stabilizer code like this. So like in the bulk, we have some Z type stabilizer and the X times CZ type stabilizers. And we have some triangular boundary conditions we can embed in some square if you want. And so this is bounded by some gapped boundary, like similar to the surface code. Like we consider such this kind of the stabilizer code. Okay, so then so what we can do is we can find a transversal T gate. The constant depth circuit, like a nearly transversal T gate on this patch of the Clifford stabilizer code. Okay, so this stabilizer code corresponds to the Z2Q case theory in 2+1D. Such identification is kind of useful for finding logical operators. And so if you are interested, we can just I can just make a technical comment. And each gapped boundary corresponds to so basically the bulk is some gauge theory, but the boundary corresponds to some boundary condition of the gauge fields. So we have some additional, for instance, if you have a Z stabilizer here, so it means that the Z equals to trivial value on the boundary. it corresponds to trivial gauge field on the boundary. Okay, so so this boundary stabilizers induces some boundary condition of the gauge fields. Okay, so this also becomes a kind of useful for constructing the logical operators in the presence of the boundaries. Okay, so that's a setup. So now we can talk about the automorphism, some symmetry of the twisted gauge theory and the associated logical operator. Okay, so so we have a twisted gauge theory, and we want to consider the automorphism of the gauge fields, which acts like this. So there are three qubits in, so red, green, and blue on each edges. So there are three colors of the gauge fields, and they act like this. So this basically tells how the power Z gets transformed under the action of the automorphism. So this can be implemented by the C naught, basically like a Z to ZZ, right? And so basically it acts like a green qubit, green Z power Z gets transformed to the diagonal like a ZZZ, right? Red and green and blue, and it acts like this. And then with this automorphism, important property, as I mentioned, is that this twist of the gauge theory has the cohomology class is preserved under the action of the automorphism. Therefore, this guy becomes the symmetry of your Clifford stabilizer code. Okay, so and this non-trivial shift of the twist becomes important to generate the non-Clifford action of the Clifford stabilizer code. So if you don't have a boundary, the symmetry operator is given by this form. So it just corresponds to transversal C naught times some additional control S. Okay, so in the bulk, it just looks like a transversal C naught times control S. And if you additionally have a boundary, we need to find some realization of the logical operator in the presence of the boundary. And then we care about some boundary condition of the gauge field, how this gauge field is realized nearby the boundary. And then we try to find some termination of the logical operators in the presence of the boundary. Okay, then we can with this input of the boundary condition, with this realization of the boundary conditions, we can find some boundary realization of the logical operators, which looks like this. So it actually turns out to be some transversal T at the bottom boundary. Okay, so eventually on this triangular patch, the finite depth constant depth circuit looks like a transverse C naught times CS times T. So this is a logical operator. So this T part becomes important, and it is actually generates a transversal T gate in your Clifford stabilizer code. Okay, so that's what we can use automorphism to generate
You had periodic boundary conditions for this. A, do you still get multiple qubits, and B?
Then the space Hilbert space doesn't really look like a qubits. It's if you consider this twisted, then the dimension of Hilbert space becomes 22. So its encoding is a bit it becomes non-trivial. But if you take this triangle, the code space is just a single qubit, and this guy becomes T gate. So thanks for the question. So this triangular patch encodes a logical qubit, just single logical qubit, this guy. So we need to carefully choose the boundary conditions. So again, depending on boundary condition, it can this setup corresponds to a single logical qubit. And this figure actually shows a realization of the power Z. So it's basically a string of the anyons, it's a string of the power Z, terminating at each of the boundaries. This guy corresponds to power Z, but actually there is no power X, so that's a difference. In the power stabilizer code, there's always a realization of power Z and power X and complete set of them. But here, because of this non-abelianness, only power Z can be realized.
You have C naught here. You have C naught in the next step.
C naught, so then basically, so we have 3 qubits per edge. So it's we can talk about transversal C naught. So right. So red, green, and blue. Yeah. No. Code consists of just a single triangular patch, but the code consists of the 3 qubits per edges. So red, green, and blue, right? Here I'm showing the colors, right? Each edge has a red, green, and blue, and this is how stabilizer looks like. And then we need to terminate the boundaries like this, like ZZ or Z or something. Yeah. It's a physical action. So it's a physical action. The logical action is just a transpose of T. Logical action is just a T on the logical qubit. Yeah. So this is a physical expression. Yeah. Is there other question? Okay, so so we can generalize this kind of bus surpassing of a Brabicanic on the Clifford-hierarchy stabilizer code in the more broader setup. So I relegate a most striking story to Ariston, but I just talk about the so maybe higher dimensional realization. We can also talk about some higher dimensional analog. So for instance, if you have 3 dimensions, we can find a transversal square root T gate, which is again the fourth hierarchy. So this logical action is a fourth hierarchy. So it's again surpasses the Brabicanic bound. So the gauge theory is a twisted Z2 gauge theory, 4 copies of Z2 and with this twist. Okay, and then if you put on a tetrahedron, you get a single logical qubit. Yeah. And then we can talk about this automorphism, which shifts a green guy like this. It's again realized by this transversal C0. And then this actually becomes the automorphism of your non-Clifford stabilizer code because it doesn't really change the homology class of the twist. Okay. And then we can find a logical operator, which is associated with this automorphism. So we can read off the physical action of the automorphism by how this homology class get changes by the action of the automorphism. So it looks like this. So basically, the physical action looks like a transverse C0 times this guy corresponds to physical control S. This guy corresponds to physical control T, and this guy corresponds to square root of T. So all of these combinations eventually at the end of the day generates a logical square root T gate and surpasses the Brabicanic bound. Okay, so that's what we can do in the generic dimensions. Okay, so if you want to use this kind of the non-Clifford gates of the non-abelian codes for the actual quantum computation, we of course need to do the code switching, right? So for instance, Clifford plus T equals universal, and we want to realize a T gates through the code switching from between the surface code and the non-abelian topological order. So this kind of the implementation of the code switching has been explored in the this IBM paper, Davidova, Bauer, and also the Dominic paper. Okay, so basically protocol is the essentially equivalent to theirs if you want to realize use this T gates for the on the surface code patch. So the protocol is that we start with a folded surface code and then do the Clifford stabilizer measurement to switch to the non-abelian codes, and then take a shot of the transversal T gate in the regime of the non-abelian codes and then switch back. Okay, so this kind of protocol can enable the logical T gate action on the folded surface code. So this is a code switching protocol. We can use this kind of the non-Clifford gate for the through the code switching to implement the T gate on the surface code patch or its generalizations. So let me just explain the comparison with the previous literature. So our contribution is just to say that on the non-abelian code we can generate logical operators which surpasses the Brabicanic bound. But if you restrict ourselves to this default stabilizer code, what we are saying is basically equivalent to the existing code switching protocol in the this Margarita Davidova paper. So basically, their protocol is basically like starting with a surface code patch and do the code switching. But we have some different way of implementing the like a code switching, like switching to the default stabilizer and the switching back to the surface code patch has a different like implementation of different. It corresponds to different gap domain wall. And actually, like one of the gap domain wall corresponds to the combination of the like a transversal T-gate and some original gap domain wall we have been using. So like eventually, like we can basically see that this transversal T-gate action is corresponds to like is essentially equivalent to the protocol they have been proposing. But yeah, our contribution is just to like provide a broader perspective of the yeah, realizing the non-Clifford operators in the realizing transversal non-Clifford surpassing the Barbecue bound. Okay. Okay, so let me just comment on like what we could potentially do in the 3-dimensional higher. So I hope that we can like realize some single shot code switching in 3 dimensions by like some suitable generalization of the gauge color code. And I haven't been able to do that, but since we have some like a transversal square T-gate in a non-abelian course, like I hope that we can do establish the single shot code switching between the color code to the non-abelian code by some coming up with a suitable generalization of the suitable subsystem version of the non-abelian code. But yeah, at this point, I don't know how to do that. But it will be very interesting over problem, I think. But meanwhile, like since we have some 5-dimensional two-form self-correcting homological codes, in this case, yeah, since this is a self-correcting property, switching can be done in a single shot. Okay, so let me just summarize my talk. So like we have just to take our message is the Clifford hierarchy logical gates corresponds to some general symmetry, which can also include some automorphism of the gauge theory. And yeah, also as an application of the automorphism, we can realize that some, for instance, a non-abelian self-correcting memory with a transversal control Z-gate, and also the family of the Clifford hierarchy stabilizer codes that enables the transversal gate in the D+1 level hierarchy within the D space dimensions, surpassing the Barbecue bound. I think the Allison will talk about the more stronger result, which surpasses completely Barbecue bound, basically. One can perform the arbitrary hierarchy. Actually, one can perform the arbitrary hierarchy gates in the 2 dimensions. Okay. And yeah, it's also related to Guanyu's talk. And so these are further development compared with my talk. And I want to ask several questions, open questions. Like for instance, it's very interesting to ask if there's some Barbecue type bounds for the varies for the non-abelian course. Like there should be some like a bounds or some trade, at least a trade-off between some hierarchy of stabilizers versus a hierarchy with logical gates, which can be implemented. I don't know how to like tackle this problem. Or like we have said, I have introduced some like fermionic toric code in my talk. And some of the non-Clifford gates of the fermionic toric code doesn't really require a triple intersection. And maybe we can use this to like get some new construction of non-Clifford gates in the quantum era LGBC. Okay, that's what I want to say. Thanks for listening. Yeah.
Thank you very much, Ryohei. Now questions or comments?
So related to this question, and maybe this is properly a question for Allison, I don't know, but can the gap between the stabilizer level and the gate level be made arbitrarily large in a fixed dimension?
I don't think so. Yeah. So Allison has an example. Maybe I should wait.
So maybe I'll just wait.
Yeah.
Okay.
Yeah.
We can get arbitrary Clifford-hierarchy logical gates in 2D, but using stabilizers at a level n-1.
Okay.
Yeah.
Cool.
So the gap remains 1, but we can bring it to 2D.
Very interesting. Yeah.
So basically, rather than space increase, we have Clifford-hierarchy.
Right. And then, so on that point, so when you're in the D dimension, Your stabilizers are, where are they? Where are they in the hierarchy? Were they level D or were they level level 3?
Within the D dimensions, the hierarchy is also D dimensions.
Okay.
Yeah.
Okay.
So so I think
it's much
aligned
sharper.
with
Yeah.
what Alison has. Yeah.
Cool.
Exactly.
Great.
Yeah.
Thanks.
So any other questions?
So what do you mean by using fermion for the QLDPC code?
Maybe we can just it's kind of similar to twisted gauge theory, but we can just change the we have a gauge theory and we can just change the statistics of the particles, right? Then we could have some other realization of the non-Clifford gauge.
The whole point of, I guess, fitting non-Clifford gauge is doing quantum computation, but where do you get fermion?
No, I'm talking about emergent fermion, like not local fermions, right? This fermion code is actually a bosonic system. Just the difference is that the stabilizer is not a CSS. The stabilizer looks like some product of the power X, the bracket stabilizer looks like addressed with a Z or something. And then then we could have some different realization. So we can kind of generalize it to the maybe broader setup. Yeah, that might be interesting. Yeah.
So like 3D toric code and fermionic toric code are kind of like very similar. So where does this like additional capacity coming from?
Additional capacity coming from the very different classification of SPT, right? For instance,
at the level of like about circuit, is it?
So at the level of circuit, this is a pumping of the P plus type superconductor. So basically we have some layer of the atomic insulators, so we can kind of construct some operator which pumps P plus type around systems. It can be achieved by some constant-ish circuit, but with exponential decays tails.
Except for the 3D, just only 3D just toric code. It's a trivial option.
Yeah, well, we have some circuit in the bosonic Z toric code as well, but it corresponds to some like a Z2 SPT, right? That has just a Z2 classification and a kind of boring action, like a CZ. It doesn't correspond to non-Clifford gate. But this guy is like a P plus IP is complicated enough. For instance, like a magnetic flux or a P plus IP, is dressed with a Majorana zero node. So associated with that, basically this P plus IP can act on an M by addressing Majorana chain. So that's why basically it has a CCZ action. So it can act on X by attaching a CZ. Yeah.
So maybe at the very layman's term, like local stabilizer has this additional to the dangling or absence of the term in the stabilizer such that when you do this actually you get to find more non-trivial operation.
Yeah. Well, that could be a possible explanation, but I'm sure. Yeah. But for fermionic thing is a much more richer. Yeah.
If I understand correctly, most of the examples here are like single logical qubit.
Well, this one, so
or like few logical qubit. I guess I'm
few logical
wondering.
qubits. Yeah, it's
I guess
a
I'm
topological
wondering
cost. Yeah,
higher rate generalization.
not quite a higher rate. Well,
right.
Yeah.
But
Brian was talking about the higher rates.
Like I guess for the results that you show here, how easy are they to generalize the higher rate? For example, I guess in 2D we also have like kind of in addition to Braviconic bounds, we have BPT type bounds. If you look at Clifford stabilizer codes, do you get any interesting
BPT
behavior?
should be quite similar, right?
Okay.
It's just caring about some locality of the cost. So it doesn't really care about the
type
of.
Okay, any other questions?
I don't know if this is a appropriate question or not, but I think like for cup product, there's a like very algebraic approach proposed by Nicholas Brugman, those people, and like there they can construct some bivariate or trivariate triscore codes, and then like they are discussing some CCT gate, and I was wondering like whether you can like give some geometric or like some, like higher form symmetry like interpretation to like those algebraically like defined cup products. Or
sorry, is there some other construction of some triple hyperproduct product calls, some gates in some product calls. So
Yeah,
also some
roughly
cup
speaking,
products.
taking three like classical codes and then taking a product, you get something like 3D-ish, and then like there you can define cup products, and then you can have like
Yeah, that's something I sort of know. But is there some? Are you talking of some other construction of the logical operator, or? But the cup product is more or less related to the SPT. Like it could be generalized to some more generic CSS code, like product or CSS code. But at least in the topological code, it's yeah, associated with SPT. So yeah.
Well, yeah, what I was wondering was like when you don't have any underlying lattice and like naively, like if your code is constructed from some chain complex, but still you have some cup product structure, and I was wondering like whether you can map that to some manifold and then like have this.
Yeah, one way to do this is like I go through the code manifold mapping, and then like we can talk about the cup product, and also yeah, there are some bunch of paper which talks about some cup product of the like yeah, after going through code manifold mapping, or like we can some paper by some Brookman and Nat was talking about the cup product directly in terms of the product of the
to a like abstract chain
chain complex, right? Yeah, well here I'm not doing that, but yeah. Yeah.
Thank you.
You can take one last question. Yeah, then maybe I can ask. You mentioned about the Bravik Coring bound. Do you think we have to develop a new theory for the non-abelian case, or is there any kind of clue that we can start with?
I have no idea, like because I think the difficulty, like one reason for the difficulty is that we don't really have a Pauli X. So usually, like so like a usual Bravik bound like is proven by taking some commutator between some Pauli operator, some other unknown logical operator. But here, like a situation is different because we don't even have a logical Pauli operator. So that's one reason for difficulty. So maybe, yeah, possible strategy is just to restrict to some specific type of cause, like a quantum double or its variance, or like then like talk about its automorphism, do something more specific. Yeah. So, but I don't know the generic how to argue generally. But there should be some. Yeah. Well, based on the like a set of example we have, there should be some trade-off between the some level of the hierarchy of stabilizers and some logical action or something like that. Yeah.
I see. Thank you. Yeah. Okay, so let's thank our speaker again.